maybe here we start recording. So taking this interpretation of I of X semicolon Y, or the mutual information between X and Y, for a communication system. So transmitter sending information to receiver through some channel in the middle. So you put X here, you receive Y here. Okay? If I want this communication system to be as reliable as possible, what do I want the mutual information between X and Y to be? A very large number or a very small number? Which one? Yes. I want to increase my knowledge about X when I read Y, right? So up to maximizing it, making it the maximum possible. So in the case of communication system, I want this to be achieved. Okay? What about the case of encryption? So I have X, right? And then it's being encrypted. And then after that, it's read by eavesdropper. Okay? And this output of the encryption is Y. So in this case, for a secure system, what do I want I, X, semicolon Y to be? As small as possible, right? And what's the smallest possible value in this case? 0. Which happens when Y is independent of X, right? When Y is independent of X, this becomes H of X. So you end up with H of X minus H of X, which is equal to 0. So in this case, I want this to go as small as possible, which is actually equal to 0. So this means that knowing Y, I got 0 knowledge about X. I didn't get any knowledge about X when I read the encrypted version of the message. Okay? This is the case of encryption. This is the case of communication. خلاص? So again, conceptually, even though by math it's not easy to figure it out, but conceptually, H of X given Y and I, X, Y, they are opposite to each other. One talks about the remaining uncertainty in X when I figured out Y. The other talks about how much I revealed about X when I read Y. How much did I know about X? How much certain I am about X when I read Y. Okay, so they are opposite to each other, even though in math they are not like, not one of them is the negative of the other or the flip of the other. They are not. But that's conceptually how they are interpreted. Okay? Discrete channel, I wouldn't really. So anyways, I will, okay. What's a discrete channel? And that's what I want you to get from this slide. A discrete channel is a channel where the input to that channel is discrete values. So the source of communication has finite and discrete possible values, okay? And the output that you read at the receiver side is still finite and has discrete values, okay? Example of this, when you communicate binary, the source of any binary information is either 1 or 0, right? And when you communicate that, you, for example, you represent the 1 by +1 voltage and the 0 by -1 voltage, because we don't really send bits. What we send is some kind of a voltage level over the channel, okay? Whether that channel is wired or wireless, okay? So you represent the 1 by +1 volt, for example, or +5, and the 0 with a -1 or a -5, whatever. Okay, so there are two possible values coming out of this, right? Then you add noise in the channel. So here we end up with the actual representation of the channel. In this case, it's just simple addition of noise. And what's noise? Noise is a random value that belongs to some Gaussian or normal distribution. Either use G or N, right? Let's use the standard normal distribution with 0 mean and some variance sigma. Okay, how does the Gaussian distribution look like? It's the bell-shaped one, right? This represents the probability density function. So what are the possible values of n? It can be from -infinity to infinity, right? But it's random, so it can be any value in that range. However, most of the time it's within this. Very rarely it goes to extreme negative or extreme positive, right? So let's say, for example, you transmit a +1, you end up with a noise, and the noise at that point was something like 6.2 volt, for example. That's just a random number coming out of noise, which is random, okay? So it's additive, so you add that to the +1, and the output is gonna be plus 7.2, right? Now that output should be mapped eventually with some rule at the receiver, right? So the receiver here is gonna use some mapping technique and eventually say this is a 1 or a 0, right? So in this case, you can think of your channel as this whole thing. You put into the input zeros and ones, you get at the output zeros and ones. This is a discrete channel, regardless of the details inside. Noise is continuous. My zeros and ones were converted to voltages in the middle, and then later on at the receiver were converted back into bits. All of that does not matter. This communication channel, from an input-output point of view, you put discrete values in the input, you get discrete values at the output, okay? And because of the noise, sometimes you can make wrong decisions. So sometimes a 1 is transmitted, but you read it here as a 0. How does this happen? That's also useful to explain here. Look at this same example. Assume that I transmitted +1 volt, and then the noise, as I mentioned, was some random value. And at this particular time when I was sending a 1, a logical 1, which is +1 volt, the noise was something like 3.7. So the output is gonna be 4.7 volt. And then at the receiver, I have a mapper that maps this back to bits, and that mapper is very simple in this particular situation. The optimal way to do this is just to assume a threshold at 0. Any voltage I receive above 0, I map it to logical 1. Any voltage I receive below 0, I map it to a logical 0. So they represent this way. A threshold detector, and if it is greater than 0, I get 1. If it is less than 0, I get logical 0, okay? And on this side, I have my transmitted signal, call it X, plus the noise value, the random noise value. So my detector is going to do what? Read this, which is what comes through the channel, the transmitted signal added to it, the noise. Transmitted signal is the voltages, +1 volt or -1 volt. And the noise is whatever random value added to it. And then at the receiver, I'm gonna compare what I receive as voltage with 0. If it's greater than 0, I will say that I detect 1. If it's less than 0, I detect 0, okay? When can an error happen? If, for example, here, instead of this, the noise at some point when a 1 volt was transmitted, the noise was something like -2.3, for example. So what's gonna be the output from the channel? 1 plus -2.3, so it's gonna be -1.3. -1.3 using this rule will give me 1 or 0? 0, right? So I will decide 0, but we see that what was transmitted actually was 1. So based on the different values of the noise and the different bits coming from the source, most of the time, if this system is designed correctly, I will do correct decision. But sometimes the noise will overwhelm my system and cause me to decide incorrectly, right? And the ratio between the incorrect over the whole transmission attempt, the number of bits that I transmitted, is what we call the bit error rate, right? Or the probability of error, okay? So this is the summary of how the discrete channel works, what's the detection of the destination, what's the transmission from the source, how does the noise actually affect my communication system. This is like a quick summary of this. I hope you studied this already in your communication course. If not, I tried to explain it here. Anyways, yes. It can take any value, but again, reasonably speaking, again, because of the electronics, for example, you cannot really have like a noise that goes to 100 volt or 200 volt or whatever. It's very rare, such that practically it will not happen, okay? Yeah, there is a typical range, which is what we use something called the noise power spectral density, which can be used with the bandwidth that you are using for communication to calculate what's the total noise power. And then you always compare what we call the signal to noise ratio for a communication system. You always compare what's the average power coming from the source divided by the noise average power, which is that power spectral density. And if that value is large enough, your communication system is very reliable and errors will be very little. If that value becomes smaller and smaller, the reliability is reduced until you reach a point where the system is totally unreliable, which means that the probability of error is half. So as if you are just randomly guessing, you are not really receiving anything. Okay. Yes, there is on practical systems, there is something called noise floor, which is the average noise power.
Like the mapping, they're relating to this, right?
Yes. Yes. Okay. One of the important models of discrete communication channel is something called the binary symmetric channel. A binary symmetric channel is a channel which has binary input, binary output. So the inputs are either 0 or 1, as you see it on this side, right? Okay. And the output is also, as a receiver, you detect either a 0 or 1, which is what we have been discussing, for example, in the previous slide, okay? And there is a possibility that a 0 gets into the channel, but it's read by the receiver as a 1, or a 1 gets into the channel and it's read by the receiver as a 0, right? These are the cases when you go through this or through that. These are the cases of error, right? If a 0 was transmitted and I figure it out as a 1, I made an error. If a 1 was transmitted and I read it as a 0, I commit an error, right? And both, whether it's an error given a 1 was transmitted or an error given a 0 was transmitted, they both have the same probability. We call it P. That's the probability of error, right? This is why we call this channel, it's binary, because inputs and outputs are binary, and symmetric, because this and this have the same probability, okay? Again, of course, over that channel, there is also a possibility of doing correct decision. If a 1-0 was transmitted and at the receiver I detect a 0, then this is correct decision. And here also we have the correct decision if a 1 was transmitted and I detected at the receiver as a 1, right? Why do we care about the binary symmetric channel? The binary symmetric channel is very simple to analyze, okay? And we'll have an exercise on that next time, inshallah, for calculating the fundamental limits that we talked about, things like the entropy, the channel capacity, all these things. And still, even though it's very simple, it's a very good representation of what happens in actual communication systems. So it allows us to use the math to do the calculations and understand the concepts. And it's not something which is a toy, which does not exist in reality. It actually represents a good amount of reality, even though it's very simple mathematically, okay? So that's why we care about the binary symmetric channel. Next time we'll see a few examples on this. Another important quantity, which is again another fundamental limit, is something called the channel capacity. The channel capacity is defined as, again, don't worry about the word supremum. You can think of this simply as maximum, okay? Not because this is a mistake, no, because the supremum is a more of it's more of a very technical mathematical term that talks about maximization, which takes into account very special cases of functions where simply taking the derivative and equating to 0 will not yield the maximum or the minimum that you are looking for. There are certain situations, particularly at the boundaries of the function. So for example, you might have, let me give you an example that clarifies this in an easier way rather than trying to explain it in an abstract form, right? If you have this function, right? And you are looking for, it's not a good one. Let me do, I don't know. Anyways, okay? And you are looking for the maximum, okay? That's easy to understand, but you might have some issues about it, okay? So if you have this function and you are looking for the maximum, right? What would you do? Typically, when you are looking for maximum and minimum, you take the derivative, equate that to 0, and check those points where you have the equation that tells you at x equals this and this and this, the derivative is equal to 0. Check each one of them to figure which one is a high point, which one is a low point, and then you pick the highest among all of them, right? Or If you have only one max, one min, then you can do second derivative, and if the second derivative is positive, this is a minimum. If the second derivative is a negative, then this is a maximum. Then you can figure out the maximum immediately, right? But doing all of that might not allow you to see that the maximum of this actually exists at this boundary point, right? So when you consider also the boundary points in addition to the bottom and the top points, this operation is called finding the supremum, okay? So it's a maximum with a little bit cautious approach, okay? It's a maximization with a little bit of cautious approach. So anyways, for you, I just wanted, when you see that expression, you understand what it means. For you, just consider it as we are looking for the maximum of the function, okay? Without really considering the sup expression. So anyways, what's the definition of the capacity in this case? The definition of the capacity is the maximum of the mutual information between the input and the output from the channel. This is what's transmitted. This is what's received, right? You try to maximize this quantity, which makes sense for any communication system. You are trying to maximize this quantity. But how do you do the maximization? Typically, when you are looking for a maximum of a function, you vary the parameter of that function until it gives you the maximum value, right? So for example, if we have f of x equals x squared, okay, and I ask you what is the maximum of f of x, you will tell me to do that, I need to change x, right, for all possible range, and then find the value of x that gives me the maximum x squared, right? That's what you do. So you vary the parameter and then read the function until you find the highest possible value for that function. Similarly here, we vary the distribution of the source. Px of x is the probability of the different symbols of the source, right? We vary that distribution with all possible variations until we find the maximum mutual information between the input and the output. What does it mean to vary the distribution? I'll give you a simple example related to binary source. In a binary source, right, the transmission is producing either 1 or 0. And we said that we said last lecture that it can be producing 1 with probability p. So accordingly, it will be producing 0 with probability 1 minus p, right? Varying the distribution in this case means testing all possible values of p from p equals 0 up to p equals 1. There is a continuum of values that p can take until you find the value of p that gives you the maximum mutual information between x and y. Okay? So that's the meaning of varying the distribution of the source. Looking for all possible probabilities for each different outcome from the source, right? Until you find the one pattern of probability that allows you to get the maximum mutual information between the input and the output of the channel. One question for you. When you do the maximization for this function by varying the values of x, the outcome that you will get out of this when you figure out where is the location of the maximum, that outcome is going to be some expression of x or just a number? Just a number, right? So the outcome that you get from the maximization is not going to be dependent on this parameter, right? It's not going to be dependent, which means that it's not going to be a function of x. It's just going to be a number because I scanned all possible values until I figured out the one that gives me the maximum. Similarly, the output that you get from doing this maximization process is no longer going to be dependent on the distribution of the source because you already varied the source until the distribution of the source until you figured out the one that gives you the max and substituted that as a number, right? So what you will get here is not going to be anymore a function of the source distribution, which means that the channel capacity, this quantity, which is the maximum of the mutual information between input and output, is no longer dependent on the source. Of course, it cannot be dependent on the destination because the destination is just reading. It doesn't do anything. It doesn't vary. Okay? So it's dependent on what? It's a property of the channel itself. the communication channel, is that channel simply an added noise? Is that noise following a particular distribution like Gaussian or whatever? Or is it a channel that multiplies something with the signal and then adds something to it and so on, right? That channel capacity is a property of the medium between the transmitter and the receiver. It's independent from whatever data you put at the transmitter, independent from that data, okay? So it only depends on what is the type of the channel, what is the type of the communication medium between transmitter and receiver, okay? So the channel capacity, definition-wise, it's the maximum mutual information between the source and the destination, where you do the maximization by varying over all possible source distribution, okay? And it's a property of the channel. And what does it mean? So now we figured out what is the channel capacity. What does it really mean? If I find a value for the channel capacity, how does this affect the design of my communication system? So the definition says that the capacity of a communication channel is defined as the maximum possible transmission rate. This is gonna be eventually calculated in bits per second, okay? If you do the math, you will find that it's calculated in bits per second, okay? Maximum possible transmission rate, okay, over the channel, okay, while being able to maintain reliable communication. Okay? So لا خليني مش طالع. طلع كده. While being able to maintain reliable communication. What does reliable communication mean? A reliable communication is defined as a communication situation where you can do something to reduce the error to a level that you desire. So if a communication system is designed, or if your communication rate allows you to use some techniques, it doesn't define what is the technique, but it just tells you that there is a way for you, there is a possibility, you can reduce the error to a desired value, even theoretically to a zero value. But of course, to get to a zero value, it becomes impractical, but not theoretically impossible, okay? However, the more practical meaning is, if you wish to reduce it to be less than a certain value, there is a practical way to do it, okay? So if a communication system does not allow you to do that, so no matter what you do, the error is gonna blow up and you cannot really control it below a certain value, then that's an unreliable communication system, okay? So what does the capacity define to me? It says that if you transmit at the rate of the capacity or less, then you are fine. Go and play with your communication system, figure out a way to reduce the error to a desired value, and you can do that, but it doesn't tell you how, okay? If you decide to transmit higher than the capacity of the channel, forget it, error is gonna blow up and you cannot control it. No matter what you do, it's gonna get larger and larger and you will lose the communication, okay? So that's another fundamental limit. Remember, the first one was the entropy, which has to do with reducing redundancy until you reach efficient communication. This one is more related to increasing transmission rate up to the level that allows you still to have reliable communication. So the other one was related to efficiency, the entropy. This one, or compression, right? This one is related to transmission rate and reliability of the communication channel, okay? Any questions so far? For the particular channel, and we are not gonna do this derivation in this course, maybe if you study a course on information theory and even a graduate course, not an undergrad course, you can study how this derivation happens, because you need to use some advanced probability technique, something called the equipartition theorem, but forget that I said this name. Anyways, we are not gonna do the derivation, but for the simple additive wide Gaussian channel, where the transmission transmitter is sending a symbol X, and the channel is only just adding noise, where this noise follows a Gaussian or a normal distribution. We call it a normal distribution. And the output here, Y, from this channel is equal to simply X added to it this random noise, right? For this channel, which is called the AWGN, additive white Gaussian noise. Additive because what you get is the addition of this randomness plus what was transmitted. Gaussian because the randomness here follows a Gaussian distribution. Noise because this parameter is a noise parameter which comes from the electronics of the receiver, right? The only word that we did not describe is white. White means that this model of the channel exists at any frequency. So the noise is across all possible frequencies. It does not change from one frequency to the other. We call that white noise because the color white in light, right, happens by adding all the colors of the spectrum or all the colors of the rainbow, right? So similarly, we assume that that's a much wider frequency. Similarly, if the noise exists in all frequency, we call it white noise, okay? That simple channel will have a capacity represented by this expression, where W is the bandwidth of communication, how much frequency range you occupy with your communication signal, and P is the power of the transmitted signal from the source. N naught is the power spectral density, the power per unit hertz of the noise that exists on that channel, of the noise that exists at the receiver side, because the channel noise is simply the noise of the electronics of the receiver, okay? And this N naught is multiplied again by the bandwidth, so this becomes, if this is power per hertz multiplied by hertz, this becomes again power, right? So this quantity, over here we have the noise power, over here we have the signal power. We call this quantity the signal to noise ratio, okay? And the channel capacity as defined by Shannon and calculated and proven mathematically for additive white Gaussian noise is given by this expression. In fact, the more accurate expression is C equals W log 1 plus SNR. So there is another added one inside this term, okay?
Which quantity did you say is the signal to noise ratio?
The P over W N naught. SNR is equal to P over W N naught. All this thing, okay? Because N naught is noise power per unit hertz. Multiplied by the one bandwidth of communication, this whole thing becomes noise power, okay? And P is signal power, so it becomes signal to noise ratio, okay? Signal power to noise power ratio. We call that SNR, okay? You also use the expression SNR in your communication, definitely, okay? So it's not, shouldn't be a new term for you. Anyways, this is just an example, so you are not gonna be required to calculate this or memorize this or whatever, okay? No, we will do that next lecture, okay? Questions are gonna happen next lecture.
You said that the output will not depend on the source. X
Uh,
and X squared.
the output, you mean the capacity?
Yeah. It
Yes.
does not depend on the source.
Yes.
But why? I mean, like, in order for you to know the X squared, you need to like know X and then square it. So it depends on the X at the end, right?
X squared, where is X squared?
The f of X equal to X squared. The example you provided.
No, here? You mean when I said if you are trying to maximize? No. When you vary this until you reach the max, the value that you will get for the max, is it going to be some expression of X or is it going to be just a value?
A value that depends on the X.
No. Because you already varied the X until you figured a value of X that gives you this. So that value is not going to vary anymore. Okay. I have an input to a function, which is X. Okay? And this plots the function. If I ask you, where is the maximum of that function? You will give me a number. Not what is the maximum, you give me a number. Is that number a function of X?
No.
Yeah, because once you evaluated it, X disappeared from the whole thing, right?
Yeah.
Yeah, that's the idea.
But before evaluating it.
Before evaluating it, you have to figure out where is the max. So you need to go through the function until you find the value that gives you the max. What you will get out of this operation is going to be a number which is no longer a function of X, right? Okay. In other meaning, you cannot tell me that the maximum is equal to this number if x equals 2, and it's equal to this number if x equals 3. There is no such a thing. You already varied x until you figured out the value of x that gives you the max, and then this produced at the output a value, which is no longer a function of x.
But it is a specific x, right?
طيب.
The value is
Let me okay. I know what you are trying to say, but how? Okay, see this. Okay. Okay. Let me show you what I mean. Okay. Imagine that this is a block which is the max of cosine x. Okay. This is a block that calculates the maximum value of cosine x. That's a block. Think of it as a block. Okay. And the input to this is x. What's going to be the output for all possible values of x? What you will get from the output? No. This is the maximum of cosine x. This is not cosine x. Which is what? What is the maximum of a cosine function? 1. So regardless of the input to this, it's going to do the math inside, and it's always going to produce to you 1, regardless of what's the input, right? Okay, you got the idea why the output from a maximization function is no longer dependent on the maximization parameter? You already kind of consumed all the values of x to figure out that the maximum of the cosine function is 1. So no matter how many inputs I put to that function, it's gonna look at, let's try to even trace the function, okay? There is always transient and steady state to anything, right? So initially this function is gonna take time to calculate. What's gonna happen to that? You vary the inputs, it's gonna say, okay, I got an input of 30 degrees, I calculated, I found that it is a half. And then an input of 60 degrees, now it's root 3 over 2, which is a little bit higher, so I maintain root 3 over 2. Transient until it figures out 1. After that, any input that goes into that function is going to produce something either equal to 1 or smaller. What's going to be the output in all these cases? 1, because that's the maximum it found so far, right? So at steady state, let's think about it this way, the output from this maximization function is going to stay always 1 no matter what you change at the input, because it has been already doing the calculations to figure out over time what is the max, and if it doesn't get any calculation of a cosine higher than that, it's not going to change the output, right? Did I make it closer or did I confuse you more?
close.
Okay, good.
But it still will never be 1 unless the x is 0 or 360.
No, unless the x passed through 0 once, right?
Yeah.
Imagine the x keeps changing all the time, right? What will happen with this? It will keep figuring out higher until it reaches 1.
It will never
And then at that point, vary the input as much as you want, it will always give you 1 at the output. So the maximization function, the eventual result of the maximization function is no longer dependent on the variations of the input, right? Okay. Let's now, so this slide is just about the channel capacity. We already covered whatever is there. Another slide that just combines the two quantities that we have discussed so far. So this is still not secrecy, just the quantities that we discussed so far. In any communication system, you have a source. The source produces data, which has a particular entropy, right? But it might not be produced in terms of how it's represented as bits at the rate of the entropy. It might have some redundancy, right? Then you use source coding, like the Huffman, to try to reduce it to a rate R, which cannot be smaller than the entropy. So that rate that you produce from the source coder is equal or greater than the entropy, right? And then you try to send that over the channel. The rate that you send data with over the channel, as we agreed, cannot be greater than the channel capacity, otherwise your communication is not reliable. This first part is the first achievement of Shannon information theory, the fact that you have two limits, one on the source encoder and one on the communication rate, right? The other achievement, which we did not really address theoretically, but you have to keep it in mind, is the genius of Shannon is not only those mathematical derivations, but the fact that he showed that you can optimally design source coder and channel coder, the one that allows you to transmit reliably and the one that allows you to remove redundancy or transmit efficiently, independent from each other. So you don't need to design them jointly for them to be optimal, right? You can design this separately and then design this separately. And if you optimize this by itself and optimize this by itself, the joint combination of both of them is going to still be optimal, okay? That allows the design of each one of them independent from the other, okay? Which is really important in designing reliable and efficient communication system. Just a catch statement on this. In the last couple of decades, by the way, this whole theorem was developed in 1945 to 48. So that was like during World War II, okay? So since then, everyone was working on those independently. In the last couple of decades, so the last 20 years or something, there was like a kind of a hype in the research community about joint design of those two together. So you design them as one combined system, more complicated, of course, in terms of doing the design. But the resulting system is typically simpler. That was the idea. So it doesn't really change the efficiency. We said the efficiency can be optimal if you design them separately, but you can reduce the system cost and the system complexity by doing joint design. Okay, that was kind of an error and it went away. Anyways, so that gives you a big picture. A more detailed communication system, particularly digital, will have source, and then there is a formatter. Formatter is what you did in your communication course to do digital to analog conversion. So, sorry, analog to digital converter in this case. So it takes your information, samples it, and then quantizes it. That's the formatter. That's what the formatter does, and then represents it in bits. Then you do source encoder, something like the Huffman, to remove redundancy. Then if you want to communicate reliably over the channel, you do something called channel encoder, and channel encoder adds redundancy again, right? So why do I remove redundancy and then add it again? Because the original redundancy that exists here was not actually carefully designed. It just exists naturally in the information coming from the source, right? But then I remove that non-optimized one to make the communication more efficient. No need to send something that I don't need to send. This is the source encoder. And then I add carefully designed bits like repetition code or block code or whatever channel coding method, so that those bits allow me to detect errors and even correct them. And that is what's meant by reliable communication, adding those channel encoder. Then one thing which we did not show in the previous block diagram is the modulator. The modulator is a functional part. This is like the QAM, BBSK, those things that you studied in communication. What do they, if you abstract them, what do they represent? They represent a piece of your system that allows you to adapt the rate of communication the way you like. So rather than sending bits as they are, you take every 2 bits and then you make them one symbol, or every 3 bits and you make them one symbol, and so on. So that allows you to adapt the communication rate, or basically separate transmission rate from source encoding rate, okay? Whatever you do in the transmitter, you reverse in the receiver. This is kind of an overview, has nothing to do with secrecy yet. The next part is what's gonna do. These 2 slides, more or less the same things, but importantly, they say that what Shannon has showed you in terms of reliable communication over the channel is the answer to the following 2 questions. The first one, can I transmit data from source to destination reliably? Yes, if you guarantee that, right? What you transmit, which is R, which is H of the source, right? H of your information, has to be less than or equal to the channel capacity. This is the minimum rate that you can do, and that minimum rate should not exceed the channel capacity. Otherwise, you cannot communicate that information through that channel. You have to look for a different channel, okay? Now, it doesn't tell you how now. It just tells you that if you guarantee that the rate is less than the capacity, you can reliably communicate. But how you can reliably communicate, this is where you start doing the, like, capitalize on the separation principle between source encoder and channel encoder, and then use the channel coding techniques to achieve reliable communication. Reiteration of what we said. No new information here, okay? Now we go to the secrecy part. Okay, time is running on us. I'll try to be slow. If you don't mind, stay with me for a few minutes after the time of the lecture, because running across this is not a good idea, okay? Remember this quantity, we have talked about it before. What is this? The conditional entropy, but at that time we were discussing two random variables x and y, right? Here we are discussing two random variables m and c. What is the difference? It's just because in the context of secrecy, rather than talking about transmitted message x and received message y, we talk about source message or information message m and cryptographic message, the one that's encrypted, c. Okay, so the relation between m and c is that m goes into some encryption function to produce the encrypted function c. So m is the information, the source information, the information that I want to send, the plain information without encryption. C is the encrypted information, encrypted message. Okay, we call this the message, we call this the encrypted message or the cryptographic message. Okay, so again, two random variables similar to x and y, but in the context of security, we call them message and cryptographic message. Okay? And again, the conditional entropy in the case of secrecy, what do you want the relation between m and c to be for a perfectly secure system? You want c to be independent from m or m independent from c. And this means that h of m given c is equal to h of m, right? This is what we call a perfect secure communication system. How can we achieve this? With something called the one-pad encryption or the one-time pad encryption. What does the one-time pad encryption do? Okay. First of all, in the context of security, this conditional entropy, we call it the equivocation function. The word equivocation means something which is being leaked. Okay. So this h of m given c is called, in the context of security, is called the equivocation function. And what we want is to maximize the equivocation function, making sure that h of m given c is equal to h of m. The encrypted message is totally unrelated to the actual information message, so that anyone who does not have the key cannot actually figure out what was my transmitted message. Okay. The best way to achieve that is using what's called the one-pad encryption. How does the one-pad encryption? Two conditions. First of all, we use a key, okay, for encryption, and we call that key by definition, we call it K, for example. Okay, and the relation between M and C, the encrypted and the unencrypted, is that C, the encrypted function, is equal to encryption, some encryption function, which is a function of the original message as well as the key. And then when those two values are plugged into some operation, the output is going to be your cryptographic message. Okay? The one-time pad, which can achieve perfect secrecy, requires two conditions on this key. The first condition is that the entropy of the key has to be greater than or equal to the entropy of your original message. So this implies that you cannot use a key which is shorter than the length of the message. Okay? Because if it's shorter, typically the entropy of the key is going to be less than the message. And if you do that, then when you combine them, the resultant entropy is going to be smaller than the entropy of the message itself. And accordingly, you have reduced the uncertainty about the message. So you are no longer perfectly secure, right? This is the first condition. This is condition number one. Condition number two is that this key has to be completely random. And they call it the one-time pad because of this completely random requirement. Completely random means two things together. Number one, it's generated from a really random source. So the source is random. Why am I saying really random source? Because, for example, what you do in MATLAB or in Python, when you try to produce a random number, this is pseudo-random. It's not actually random because it's produced using some polynomial, and it's not one value is not completely independent from the other. So what you produce there is an approximation to a random, but what is required here is a truly random key. Okay, this can be done, for example, by generating the key. A good approximation to this can be done by generating the key from sampling a certain natural quantity, like reading the temperature, and based on the variation of the temperature, I produce the key, right? Okay. The second part of completely random is that for every new message, you have to generate a new key, right? So that's basically the second condition on perfect secrecy that Shannon puts. Okay. Where is the impracticality of this system? Number one, the difficulty of producing something which is truly random. But the more important impracticality comes where?
The key يكون عند الريسيفر.
Yeah, exactly. So that random key has to be shared somehow with the receiver. How can you do that? I mean, the only way is to figure out a way to communicate the key to the receiver without the eavesdropper listening to the key, which brings you to try to encrypt the key. But if you try to encrypt the key, you have to use another key, and then you get into an practically impossible loop, right? Like practically, yes, you can do an approximation of this, but you cannot really do the perfect secrecy system in real life. There are good approximations to this by using some key value sampled from the environment, and it's taken from a value that's read by the transmitter and the receiver only, right? At any point in time without a need for those two to exchange that value together. Let me give you an example of this. Something called physical layer secrecy using channel gain. So physical layer secrecy.
Doctor, before you complete, the key here, is it the same as the shared key?
Yeah, that's the one. The key that both transmitter and receiver should know, but eavesdropper should not know.
The one that is here, right?
The key here, yes. Okay. So physical layer secrecy, what does it do? If you have two communicating parties, particularly in a fading channel, you studied fading channel in your communication course, right? You did. Channel that varies with time. The amplitude of the channel varies with time, right? You studied that because of multipath communication and things like that. You studied something called fading channel. I hope so. Anyways, what does this represent? If you are sending an information here, X, the channel is not just adding noise, but it's actually what you receive here is X multiplied by some channel gain H and then added to it noise N. Okay? This H is a function of the environment and it's random. It's not deterministic. Okay. However, it's seen by those two parties as the same. So the channel, when you communicate this way or that way, it's called reciprocal. So both of them sees the same channel gain. And there are ways to measure it to some accuracy, but both of them can measure it directly from the environment without really exchanging any information together. Okay? So now if you use this, which is only known jointly between those, if you have another communicating party, the channel between this and this is different from this, and the channel between this and this is different from this and different from this, right? The channel is only defined at the two ends that are communicating to each other. So now you have some random value which is jointly known between the transmitter and the receiver, but definitely not known for the eavesdropper. Okay? And they don't need to exchange it. It's available physically to each one of them from the environment directly. Okay? Of course, they don't see exactly the same value. There are some fluctuations on both sides, particularly due to noise, right? That makes it slightly different, but using some quantization, you can remove these differences. But when you do that, you reduce the entropy a little bit, right? So it become, again, that's a good approximation, but not completely perfect, okay? Anyways, the important part here was not really the physical layer secrecy, but just to tell you that as per Shannon's definition, for a perfectly secure system, we want the equivocation to be the highest possible, right? And in order to do that, it has to be equal to the entropy of the unencrypted message. And the only way to do this is that the encrypted message is completely independent from the unencrypted. And the theoretical way to achieve that is using the one-time keypad. One-time keypad has those two important properties of the key itself. The key is completely random, so it's deduced from a true random source, and it's changed every time with every message. And the other thing is the entropy of the key has to be greater than the entropy of the message itself, okay? Now, this allows us to do perfect secrecy, but how do we measure a secrecy of a communication system? This is the last part, okay? If you have a communicating party, a receiving party, and an eavesdropper, okay? Remember, when you communicate from transmitter, so that's Alice, this is Bob, this is Eve, right? Here, between Alice and Bob, you have the mutual information of the transmitted signal X and the received signal Y. And the relation between X and Y is simply just a difference of a noise, for example, okay? On the other side, you have an eavesdropper. Assume that the channel to the eavesdropper is this channel, right? And simply what the eavesdropper is reading, we call it Z, because it's going through a different channel. So even if it is just due to noise, it's reading something slightly different, right? So the mutual information here is IX semicolon Z, okay? What you want is make this as small as possible, so nothing is revealed to Eve, right? And make this as large as possible, so everything is revealed to Bob. The difference between those two quantities, right, is what we call the leakage amount. And that leakage amount, the secure amount, okay? And that secure amount, this is called the leakage. And this is called the actual communication. The difference between them is called the secure communication amount. And what we want is to maximize this difference, right? I want to make sure that the difference between this and this is maximized as we see here. And that difference, when maximized, we call it the secrecy capacity. Remember, the capacity was the maximum rate to communicate without anything related to security. Secrecy capacity, the maximum rate to be able to securely communicate. Okay? Of course, this is in general smaller than or equal to just the capacity of this channel without any security considerations. So if you want to secure over a particular channel, you need to make sure that the difference between the mutual, so you need to maximize the mutual information from Alice to Bob and reduce as much as possible the mutual information between Alice and Eve, right? Okay. How can you do that? Many ways to do it. One way is to make sure that one channel is weaker than the other. If this channel has smaller capacity, call it CE, than this channel, then definitely the difference between those is going to be a positive value here, and you can securely communicate with a positive rate, right? Or the other way, when you use a key encryption and decryption, what do you effectively do? The guy who has the decryption here eventually will have a high IX semicolon Y, right? Because it can decrypt, and the only effect remaining is just the noise. The guy who doesn't have a key will have a very low value of X semicolon Z, because Z is not only affected by noise, but I don't have a key. So Z is no longer that much related to X, right? So this makes this channel weaker. So encryption is just one way to make the leakage to the eavesdropper weaker. But the general measure is actually done by this quantity.
How can we control the channel?
One way, practically, that's a very good question. In the direction of, imagine this, if I have a transmitter, that's gonna be the last question and the last thing to say today, okay? Imagine that you have a multi-antenna transmitter and you have multi-antenna receiver here, and Eve's is also multi-antenna receiver, okay? I can, for example, use some of these antennas to direct my information only to this guy, right? So now the amount that comes in this direction is very small because it uses a side lobe of the antenna. Not only that, I can use the remaining antennas to direct noise towards this jamming. So now I direct pure signal to Bob, while in the direction of Eve, the pure signal becomes much weaker because I already directed the beam in this direction, and even I add some jamming to that guy. This makes the signal to noise ratio here much lower, which means that the channel is much weaker.
But
Yeah, that's the issue. So to do that, you need to know the direction. So that's possible when you can spot where is the eavesdropper. If you don't, encryption is the way to go, for example.
Can we
Okay?
just jam in different ways?
That's another direction. So one other way is to inject noise everywhere except in the direction of my intended receiver. So anyone who's away from the intended receiver is gonna be jammed, and this guy only is gonna be able to listen to my message. Okay, so there are many techniques that can be applied to this, but the main principle comes from this secrecy capacity principle. خلاص؟